Okay, so for more than 60 years, there was this theoretical speed limit in computer science, a barrier that pretty much everyone thought was just, unbreakable. But then a team of researchers comes along and does what everyone thought was impossible. And I mean, they didn't just inch past the limit, they smashed right through it. So yeah, let's dive into the algorithm that just completely rewrote the rulebook.
So think about it. Every single time you pull up Google Maps or Waze, you're asking this one fundamental question that has, obsessed computer scientists for decades. What is the absolute fastest way to get from point A to point B? It seems so simple, right? But behind that little blue line on your screen, there's this incredible computational battle that's been raging since, well, basically the dawn of the computer age. This quest, officially, it's called the shortest path problem. But look, it's not just about your map app. We're talking about how data packets zip through the internet, how shipping companies manage their logistics, even how social networks are analyzed. So you can imagine, finding the most efficient solution here has always been a huge deal. So the classic version of this puzzle is called the single source shortest path problem, or SSSP for short. And the idea is pretty simple. You start at one single point, that's your source, and your goal is to figure out the shortest possible path to every other point in the whole network. I mean, this is basically the bedrock of modern navigation and network theory. And believe it or not, for the last 60 plus years, this whole field has been completely dominated by just two legendary algorithms. And get this, they were both developed way, way back in the late 1950s. So let's meet the reigning champs. All right, first up, we've got Dijkstra's algorithm. The best way to think about this one is as the perfectionist. Seriously, it works kind of like a perfect ripple spreading out in a pond. It starts at your location, and then it always, and I mean always, expands to the very next closest point it hasn't seen yet. It's super elegant, super precise, and for a lot of common situations, it's incredibly efficient. Now, the other heavyweight in the ring is the Bellman-Ford algorithm. And this one, it's more of a workhorse. It doesn't bother with that meticulous, find the next closest point thing. Nah, it just methodically checks every single path, over and over and over again, slowly making its guesses better until it finally lands on the shortest routes. Yeah, it's slower, but man, is it robust. Okay, so here's the crucial takeaway. Dijkstra is fast, it's elegant, but there's a catch. To be so darn precise, it has to constantly sort all of its possible next moves to find the absolute closest one. And that sorting, well, that creates a major bottleneck. Bellman-Ford, on the other hand, totally avoids that sorting, but it's way slower because it's just brute forcing the whole thing. So for decades, that was your choice, the elegant perfectionist or the slow and steady workhorse. Pick your poison. And that catch with Dijkstra's algorithm? Yeah, that wasn't just some minor inconvenience. It ended up creating what computer scientists genuinely believed was a fundamental, like an unbeatable wall for this entire category of problems. I mean, just listen to this. The researchers behind this new breakthrough, they say it right in their paper. The community just believed this barrier existed. It was a fact of life. The thinking was, you just couldn't solve the shortest path problem any faster than you could sort all the points. And that was that. End of story. And this really gets to the heart of it all. The very thing that made Dijkstra's algorithm so brilliant, that perfect step-by-step sorting, was also its biggest weakness. It's kind of ironic, right? It literally created a speed limit that nobody could figure out how to break for over 50 years. And right here, this is what that barrier looks like in math terms. Don't worry, just think of it as a formula for how long the algorithm takes to run. The really important part is that bit at the end, the log n. That little piece right there, that represents the time it takes to do all that perfect sorting. And for decades, that sorting cost was considered the unbreakable speed limit. So how in the world do you break an unbreakable barrier? Well, you don't play by the old rules. The amazing thing about this new algorithm is that it doesn't try to be just a better Dijkstra or a faster Bellman-Ford. Nope, it creates this super clever hybrid that pulls the best from both of them. And the core idea behind it is kind of brilliant in its simplicity. It's basically asking, what if? What if you didn't have to sort everything perfectly? What if you could use the raw brute force power of Bellman-Ford to handle all the easy stuff, and then save the super precise logic of Dijkstra for only the most important decisions? And here's how this brilliant new strategy works. It's basically a four-step plan. First, it scouts. It uses a few quick and dirty Bellman-Ford steps to find all the easy win paths without any sorting. Then it identifies pivots. Based on what it found scouting, it picks out the few truly important crossroads. After that, it conquers by unleashing that powerful, precise Dijkstra-style logic on only that small set of pivots. And finally, it just divides and repeats, breaking the big problem down into smaller, more manageable chunks until the whole thing is solved. So cool.
And the result of all that cleverness? A new speed record. Remember that log n part, the sorting cost? Well, look at this. It's been replaced by a much, much smaller term. We're not talking about a small tweak here. This is a fundamental, ground-up change in how long it takes to solve this problem. Just to give you a picture of what this means, check out this chart. It's visualizing that core bottleneck we've been talking about. For a really big network, the complexity of the new algorithm's bottleneck is less than half of the old ones. And when you get to truly massive, complex networks, I mean, the difference is just astronomical. It is a massive leap forward. Okay, so it's faster. Big deal, right? Why does this really matter? Well, because this isn't just about getting your pizza delivered 2 seconds quicker. This is about fundamentally changing what we all thought was even possible in the first place. I mean, for starters, it's a huge theoretical milestone. It just proved a 60-year-old assumption was flat out wrong. That's big. It also lays a new foundation for innovation in, well, everything, from logistics to AI. Plus, it's what's called a deterministic algorithm. All that really means is that it's reliable, it's predictable, it gives you the best answer every single time. And finally, this helps future-proof our entire digital world for the insanely complex networks that are coming. You know, at the end of the day, the story of this algorithm is just this amazing reminder that impossible is often just a problem that's waiting for someone to look at it from a new angle. It really makes you wonder, right? What other unbreakable walls are still out there, just waiting for the next clever idea to come along and completely tear them